let's talk about numbers. Specifically, let's talk about the counting numbers 0, 1, 2, 3, and so on. You can perform operations on these numbers, like addition and subtraction, and they're very useful when communicating with other people. But have you ever stopped to think about what the number 1, for instance, actually is? First off, I'm not talking about the numeral 1. A numeral is just a symbol that we use to talk about the idea of a number. It's a sort of shorthand in the same way that your name is. Your name describes you and lets others refer to you easily. The Romans used letters to describe their numbers, and these are referred to as Roman numerals. So, keeping that in mind, what is the number 1? Well, first we have to talk about sets. A set is just a collection of distinct objects of any kind, and we can tell what objects are in the set itself. The objects in a set are called elements, and we put the elements of a set inside curly braces, like this. For example, we could have a set of 3 names, Bob, Alice, and Jane, and we would denote it like this. A mathematician named John von Neumann proposed that we could make every number by starting with the empty set, or the set with nothing in it, and sort of climbing our way up a ladder like this. It looks confusing, but let's take it step by step. The number 0 is going to be the empty set, denoted by the empty braces. Then the number 1 is the set containing 0, which, because 0 is the empty set, the number 1 is the set containing the empty set. And we want to continue doing this for every number. And we want to do it that way because we're trying to define the numbers in terms of sets. This construction is pretty straightforward and offers simple reasons why, for instance, the number 1 is less than 2, or when you have any 2 distinct numbers, one is always larger than the other. However, the explanation does fall a little bit short because it seems artificial. 0 is the empty set because I say so. Then everything else kind of follows from there. Another mathematician, Neumann and Frege, is going to help us out with this. His concept of numbers is based on equivalent sets. So, now let's take 2 sets, A, B, C, and 1, 2, 3. And we're going to create a correspondence between them like this. So A goes with 1, B goes with 2, and C goes with 3. Obviously, this isn't the only way that we can match these elements up, but that doesn't really matter. What we're interested in is called a one-to-one correspondence. That means each element in the first set is matched up with exactly one element in the second set, and each element in the second set is matched up with exactly one element in the first set. Does it make sense? That's why the arrows go both ways. Because there is a one-to-one correspondence between these 2 sets, there's some property that the sets share, and that property is called a cardinal number. Here, our 2 sets share the cardinal number 3, and we write it, as you guessed, the number 3. So, keeping all of this in mind, what is a number? A number is the property of sets which is common to all sets in one-to-one correspondence with each other. Okay, that sounds confusing, I know. But if you've been following the explanation so far, it's pretty straightforward. It's just that when we take all possible sets that are in one-to-one correspondence with each other, so like our sets A, B, C, and 1, 2, 3 before, we're going to take those to start with, and then every other set that can be matched up in the same way with those. And when you put all those together, they all share one property, and that property is a number. So, why would we want to do something like this? Why is it useful? Well, first, it makes sense to consider a number as a set because numbers are often used to describe or count the number of objects that are in a group. Then, if we want to extend our concept of numbers to use equivalent sets, that makes sense too. If we think about how before numbers are really invented and worked on, a shepherd might keep track of his sheep in a flock by taking one stone and keeping it in his pocket for every sheep. and then at the end of the day you can count off 1 stone per sheep. And so this is kind of our correspondence between the equivalent sets. Finally, this construction also gives us explanatory power when it comes to infinite sets, which I'm not going to get into today. I hope that this has offered a little bit more explanation about where our numbers come from, and good luck exploring with everything else you come across.